The next time you board a wide-body commercial aircraft, before you sit down, before you stow your bag, before the door closes, look out the window at the engine hanging under the wing. That object, that cylinder of metal approximately 3 meters in diameter, is operating at internal temperatures that exceed the surface of the sun. Not the core of the sun, the surface. The surface of the sun is approximately 5,500 degrees Celsius. The combustion temperature inside the GE9X turbofan engine, the engine that powers the Boeing 777X, reaches 1,700 degrees Celsius in its combustion chamber. But the first stage turbine blades, immediately downstream of the combustion chamber, the blades that must survive in direct contact with those combustion gases, must operate in gas temperatures that exceed their own melting point. Read that again. The turbine blades operate in gas temperatures that are higher than the temperature at which the metal they are made of becomes liquid. By the laws of physics as most people understand them, those blades should not exist. They should have melted the first time the engine was started. That they have not, that they run for tens of thousands of hours without melting, is one of the most extraordinary engineering achievements in the history of human civilization, and it is hanging under the wing of your flight right now.
To understand how this is possible, you need to understand what a modern turbofan engine actually is, and why the numbers associated with it should be impossible. The GE9X 105B1A, the most powerful commercial aircraft engine ever certified, produces 105,000 pounds of thrust. To give that number physical meaning, the combined thrust of all 4 engines on the Saturn V rocket that launched humans to the moon was 7,600,000 pounds of thrust. The GE9X produces 105,000 pounds from a single engine. The Boeing 777X has 2 of them. But thrust is not the most revealing number. The power output is. The GE9X generates approximately 100,000 shaft horsepower during takeoff conditions. 100,000 horsepower from a single engine. The entire electrical generating capacity of Iceland, a country of 370,000 people, is approximately 3,000 megawatts. One GE9X engine at takeoff power generates approximately 75 megawatts of equivalent power. 4 of them together would power a mid-sized city. And this engine, producing power at scales previously associated only with industrial power plants, weighs approximately 10,000 kilograms, fits within a nacelle 3 meters in diameter, has a fan diameter of 3.4 meters, nearly 11 feet, spinning at over 2,500 RPM. The fan tip speed during takeoff, approaching the speed of sound. The outer edge of the fan blade is moving at approximately Mach 0.9, while the blade root remains stationary at the hub. The aerodynamic and structural engineering required to design a blade that operates at near-sonic speeds at its tip, while experiencing completely different airflow conditions at its root, is a solved problem that required 50 years of computational and material science to solve.
Now return to the turbine blades. The first-stage high-pressure turbine blades in a modern commercial engine are the most thermally stressed mechanical components ever manufactured for routine use. The gas temperature at the inlet to the first-stage turbine, immediately downstream of the combustion chamber, exceeds 1,700 degrees Celsius in modern engines. Nickel superalloy, the material the blades are made of, begins to lose structural integrity at approximately 1,300 degrees Celsius. The blades should melt. They do not melt because of 3 simultaneous engineering solutions that each individually represent decades of research, and together represent a physical impossibility made routine. Solution 1. Single crystal metallurgy. Each turbine blade is cast as a single crystal of nickel superalloy, not a polycrystalline metal with grain boundaries that would provide paths for high-temperature creep and fracture, but a single continuous crystal lattice grown from a single seed crystal in a precisely controlled furnace, oriented specifically to maximize strength in the direction of the centrifugal load the spinning blade experiences. Growing a single crystal component the size of a human palm requires a process so precise that even a single boundary defect in the crystal structure will cause the blade to fail in service. Every blade is individually inspected using X-ray crystallography before installation. Solution 2. Thermal barrier coating. The blade surface is coated with a ceramic compound, yttria-stabilized zirconia, approximately 125 micrometers thick. This ceramic coating has a thermal conductivity so low that it creates a temperature drop of several hundred degrees between the gas environment and the blade surface, even though the coating itself is thinner than 2 human hairs. Solution 3. Film cooling. The blade is hollow. Hundreds of microscopic channels, machined through the interior of each blade, carry compressed air, bled from the compressor stages, through the blade structure and out through tiny holes on the leading edge, trailing edge, and blade surface. This air forms a thin film of cooler gas between the hot combustion products and the blade surface. A film so thin it is measured in microns, but sufficient to reduce the effective temperature at the blade surface by 200 to 300 degrees Celsius. The combination of these three systems allows a blade made of material that melts at 1300 degrees to survive continuously in a gas environment of 1700 degrees for tens of thousands of hours, at rotational speeds exceeding 10,000 RPM, under centrifugal loads that place each blade under tension equivalent to hanging 12 tons from its root.
The manufacturing precision required to produce a modern turbofan engine is a story that makes the engineering performance even more extraordinary. The film cooling holes in a first-stage turbine blade, the microscopic channels that carry cooling air to the blade surface, are drilled by laser. Not because laser drilling is the most convenient method, because the holes are too small to be produced by any other means. The typical diameter of a cooling hole, 0.3 to 0.5 millimeters. A human hair is approximately 0.07 millimeters. Each blade has between 20 and 100 of these holes. A single engine has dozens of blades. Each hole must be positioned with a positional accuracy of less than 0.05 millimeters, or the cooling effectiveness of the entire blade is compromised. The fan blades, the large blades at the front of the engine, present a completely different manufacturing challenge. The GE9X fan blades are manufactured from carbon fiber composite, not metal. Each blade is built up from hundreds of layers of carbon fiber pre-impregnated with epoxy resin, laid up in a precise orientation pattern, and cured under heat and pressure in an autoclave. The resulting structure weighs significantly less than an equivalent metal blade, but must survive bird strikes at takeoff speeds, hailstones at cruise altitude, the catastrophic loss of a single blade, which the engine must survive without destroying the aircraft. The FAA's fan blade containment requirement, that the engine nacelle must contain a failed fan blade without penetrating the aircraft structure, is tested by actually firing a blade from a running engine and confirming the nacelle stops it from exiting. This test is performed on every new engine design. The nacelle must survive, every time. The tolerances throughout a modern commercial turbofan engine are so precise that the gap between rotating compressor blades and the static engine casing is measured in tenths of a millimeter, the thickness of a piece of paper. Thermal expansion of the engine during operation changes every component's dimensions by amounts that must be calculated, predicted, and accommodated, because the engine that fits perfectly cold would rub catastrophically hot if this were not accounted for. The engineering of a modern turbofan engine represents the highest concentration of precision manufacturing in any object routinely produced by human industry.
The Rolls-Royce Trent XWB, the engine that powers the Airbus A350, holds the record as the world's most efficient large turbofan engine ever produced. Its thermal efficiency, the percentage of the chemical energy in its fuel that is converted to useful thrust, is approximately 50%. That number requires context. The average internal combustion engine in a passenger car achieves approximately 25 to 30% thermal efficiency. The Rolls-Royce Trent XWB converts fuel energy to thrust at twice the efficiency of the engine that powers your car. Its bypass ratio, the ratio of air that flows around the core to air that flows through it, is approximately 9.3 to 1. For every kilogram of air that passes through the combustion system, 9.3 kilograms bypass it entirely, accelerated by the fan at the front of the engine. This architecture is what makes the modern turbofan so efficient. Moving a large mass of air at relatively low velocity produces more thrust per unit of fuel than moving a small mass at very high velocity. The physics were understood from the earliest days of jet aviation. Achieving them in a package that fits under an aircraft wing, sustains 50,000 hours of operation, survives the physical extremes described in the last few minutes, and costs less per seat mile than any previous form of long-range transportation. That took 60 years of engineering. And the result, this object hanging under the wing, hotter than the sun's surface in its most stressed components, producing the equivalent power of a small city's electricity grid, manufactured to tolerances measured in human hair widths, costs approximately $40 million. One engine. And it will be replaced, on schedule, on condition, before it fails, because the airline's maintenance system tracks every hour of its operation and knows to within engineering certainty when its service life approaches its limit. The object you glanced at through the departure gate window this morning is the most complex, most extreme, and most reliable machine ever routinely manufactured by human civilization. Follow for more about the physics operating at the absolute boundary of what matter can withstand on every commercial flight you have ever taken.